Okay, welcome back again. I started to give this example, but actually it is easier to first prove an additional statement about these alpha x's that we constructed. These integral curves associated with left invariant vector fields on the Lie groups. And it turns out that these integral curves have another characterization. So, definition, we are going to define the notion of a one-parameter subgroup of a Lie group. A one-parameter subgroup of G is a map alpha, or I should say is a smooth group homomorphism alpha from the reals with addition and 0 to the Lie group G. Now this terminology is a bit misleading because I'm talking about a subgroup, but I'm not requiring that alpha is injective. So that means, and there are situations where alpha is not injective. We'll come back to that later. For instance, so then the image of alpha would be a circle which would be run through indefinitely if the time parameter goes to infinity in R. So this is not necessarily injective. It is just a smooth map having the properties that first of all alpha of 0 is the identity element, and secondly alpha of s plus t is alpha s times alpha t. So these are the characterizing properties. And of course smoothness. Now the alpha x that we have constructed by using left invariant vector fields satisfied these conditions, because this was the initial condition and this was the condition that we established. So alpha x is an example of a one-parameter subgroup. Lemma. For all x in the tangent space, alpha x is a one-parameter subgroup. This is what we established. But now the beauty is that these are all. So any one-parameter subgroup is of this particular form. So this is one. Second, if alpha is a one-parameter subgroup, then alpha is of the form alpha sub y. And how do we get y? Well, this should be the tangent vector at the identity element. So the velocity vector at 0. Where y is given by the derivative of alpha at 0. Proof. I mean, this is so important that I want to present the proof. It also gives an impression of the kind of techniques that is being used here. First of all, one has been established already, so we don't have to prove to give a proof of this fact anymore. So let's establish 2. So let alpha be one-parameter subgroup. Now to show that alpha is the integral curve, the maximal integral curve of a left invariant vector field, I have to say something about the derivative of alpha. Okay, so alpha prime of t is the same as the d dt of alpha of t. And this is the same as the DDS at s is 0 of alpha of t plus s. Now one way to see this is by application of the chain rule. But of course, if you think of differential calculus in Rn, then this is well known, right? And it follows immediately from the definition by using, by doing a substitution in the limit for the difference quotient. But here one can use the chain rule to see that this is true. And then we use that alpha is a one parameter subgroup. In other words, this can be rewritten as a product. So then this is the DDS at s is 0 of the product alpha s times alpha t. Now alpha s times alpha t can be viewed as a map applied to alpha t. Oh, I would rather put it like alpha t times alpha s. So it's a map applied to alpha s. It's left translation by alpha t applied to alpha of s. So we have the derivative of a composition, and the derivative of a composition is given by the chain rule. So by the chain rule will be used lots of times. I will say more about the chain rule a bit later. So this is really, so how is the chain rule applied here? Well, we have to take the tangent map of this left translation at the image point here, which is the identity element. Alpha of 0 is the identity element. So it's the tangent map at the identity element of lambda of alpha t. And it should be applied to the derivative of alpha at s is 0. So it should be applied at alpha to alpha prime is 0. But this was the defining formula for a left invariant vector field. This is the same as the left invariant vector field associated with the tangent vector alpha prime of 0 in the point alpha of t. So now we have this equation. Alpha prime of t is the left invariant vector field associated with this tangent vector applied to alpha of t. In other words, alpha is an integral curve. Its domain of definition is all of R, because this is contained in the definition of one parameter subgroup. And alpha of 0 is the identity element. So alpha is the maximal integral curve for v sub y and initial point identity element with y equal to the tangent vector at 0. Now the maximal integral curve is unique, and we denoted it by alpha y. So this implies that alpha is alpha y. End of proof. Good. So now we know all one parameter subgroups. And what we are going to do now, and now you see why I first wanted to do this, because now I'm going to look at that particular example, the particular example of V, a finite dimensional real linear space, G is the general linear group of V, so it's tangent space at the neutral element may be identified with the space of all linear maps from V to itself. Now suppose that we have a linear map Y from V to itself, then look at alpha of t is e to the ty. So here we take the exponential, the usual exponential of a matrix. So it's defined by a power series, if you like. And we know that this exponential satisfies the differential equation. But we also know that it has a multiplicative. The important fact here is that it has a multiplicative factor. This, first of all, this defines an invertible matrix, so it belongs to G. It is smooth in the parameter t. Its value at 0 is e to the 0 is the identity matrix, which is the neutral element of G. And it satisfies the multiplicative property that this is equal to the composition or the product in that in this particular group of the two exponentials for all s and t. So it's a one-parameter subgroup, and we know that each one-parameter subgroup has to be of a specific form. And what is the form? Well, what is the d dt? So what is alpha prime of 0? Alpha prime of 0 is so what is the derivative of this exponential? Well, that's e to the ty times y at t is 0, which is equal to y. So what this shows is that in this particular example, this exponential is the integral curve for the left invariant vector field that is determined by y. So the conclusion is that e to the ty is equal to alpha sub y of t, and this is true for all linear maps from V to itself and for all real numbers t. This is the conclusion. But that means that this exponential can be expressed in terms of alpha y. E to the y is alpha y of 1. Now mind you, we are in a particular situation, a particular example, where we have a way of defining the exponential by using a power series. But in the general setting of Lie groups, we have no way to do that. We do not have an ambient linear space in which we can use addition or power series. We just don't have that. But we do have left invariant vector fields, we do have their integral curves, and we do have one-parameter subgroups. So now the idea is to define the exponential map by using this formula in the general context. Definition: exp the map, the exponential map from the tangent space at the identity element to G is defined by mapping the vector y to take the corresponding one-parameter subgroup and evaluate in 1. Of course, it is a good idea to visualize what we have been doing here. So we have our Lie group G, we have identity elements E, we have tangent vector y, we use left translation to produce a vector field, invariant vector field, then we have a maximal integral curve, and then what we do is we evaluate at t is 1, and then in some sense we get the point of the Lie group for which this y is the best approximation. And this is the exp of y. And I'm using the symbol exp on purpose, I'm not using, sometimes in the literature one finds the expression e to the y, but I'm avoiding this here because I want to emphasize that it is not a power of a number. It's really produced as a solution of a differential equation here. Okay. Now there is a few properties of the exponential map that you should know, and which I'm going to list. I don't have the time to really go through all details of the proof here, but I think that really the proof is by the same principles as those that we have discussed in the first hour. But a few important properties is lemma. First of all, this map is smooth. Well, basically this is a statement about the dependence of solutions of differential equations on parameters. We have a smooth system of differential equations, and this is really the statement that the solutions that we have produced depend smoothly on the initial data. Secondly, exp of tx is the same as alpha x of t. Well, this is by showing that exp of tx can be interpreted as, satisfies the differential equation needed to show that this is an integral curve for the left invariant vector field. That's basically the proof. And so it's the same principle as we've seen before. Third, exp of s plus tx is exp as of x times exp t of x, where here we use the product in the group G. Now this is of course an immediate consequence of 2 because we know the same equation for alpha x of t. Right? Alpha x is a one parameter subgroup. 4, that the tangent map at the 0 element, so 0 is an element of the tangent space, which is a linear space. The tangent map at 0 of the exponential map is, well, the exponential map is a map from the tangent space at the identity element to G. The tangent space at 0 of this linear space may be identified with the linear space itself. That's the general principle. And then of course we have that the exponential of 0 is the identity element. So the tangent space at the image point of G is the tangent space at the identity element again. So this map is a map from the tangent space to itself, or rather it has a canonical interpretation as a map from the tangent space at the identity element to itself, and then the statement is that this is the identity map equals the identity map of that tangent space. And so in particular, by application of the inverse function theorem, this means that the exponential map is a local diffeomorphism mapping so it's a diffeomorphism from a suitable neighborhood of 0 in the tangent space to a suitable neighborhood of the identity element in G. So hence, exponential map is a local diffeomorphism at 0. Okay, good. So details of the proof of this lemma are available in the lecture notes. Now, this this rather canonical way of introducing the exponential map through one parameter subgroups, or through invariant vector fields if you like. This has a very, very nice consequence, which is extremely important for the further development of the theory. And that is that there is a very natural relation with homomorphisms. So suppose we have two Lie groups, and this is something that is so important that I'm going to prove it again on the blackboard. Suppose that we have a homomorphism of Lie groups. Phi. Then the following diagram commutes. We have G, phi maps G to H. We have the exponential maps of G from the tangent space as the identity element, and we have the exponential map of H here from the tangent space to H at the identity element, and we do have a map here. I mean, the only decent map that we can write down is the tangent map of phi. Phi of the identity element of G is the identity element of H, because phi is a group homomorphism, so the tangent map will be a linear map between these linear spaces. And now the statement is that this diagram commutes, and by this we mean that in whichever way we take the composition of arrows, going from one of these to another, the result will be the same. So commutativity means that this composition of maps should be the same as this composition of maps. And saying that a diagram is commutative is indicated by putting an arrow like this. So this means the diagram is commutative, and which in turn means precisely that the composition of phi and the exponential of G is equal to first applying the tangent map of phi and then applying the exponential map of H. Now this is I hope that you see the beauty of this. Right? It's really, not only do we have a group structure preserving map here, but it induces on the tangent level a structure preserving map here relative to the exponentials. Okay, proof is extremely simple now, and it's a completely natural argument. This is hard work. But I'm paid for it. And it's a joy to do, which is maybe more important. Okay, so how do we prove this? Well, by fixing an element here, applying these maps and showing that the results are equal. But we do a bit more. We are going to use a one parameter subgroup here. So fix, or let X be a given element in the tangent space in the lower left corner. Then we can look at alpha sub X of T is X of Tx. This is a one parameter subgroup in G, right? Now if we apply a group homomorphism to a one parameter subgroup in G, the composition of two homomorphisms is a homomorphism again. So then we get a one parameter subgroup of H. So phi of alpha x of t is a one-parameter subgroup of H. So in an ad I would say that I cannot make things more natural than they are here. This is really extremely natural. Now we do have the result that we know what the one-parameter subgroups are. So this has to be equal to a one-parameter subgroup of H, which is given by an element Z, where that element Z is found by taking the derivative of this expression with respect to t at the point t is 0. This can be calculated by using the chain rule. We take the chain rule in the image point, which is the identity element, and we apply this to the derivative of alpha x of t with respect to t at t is 0. So alpha x prime at 0. But this is x. And so what we see is that z is the image of x under the tangent map. So the conclusion of this is that phi of x, the exponential map of g, tx, which is this expression, equals that expression, which is equal to the exp of h applied to tz, that this z is equal to te phi applied to x. Now take a particular value for t. Take t as 1. If we take t as 1, we get the phi of xg of x is equal to the exp of te of phi of x. And this is exactly the commutativity that we set out for. So substitute t is 1, and this gives us the formula that we have been looking for. Now take t is 1, and this gives us the result. Okay, now we really came to the end of the... Yes?
Can you tell me why Z is equal to this derivative?
This was part of the statement about one-parameter subgroups. If you have a one-parameter subgroup, it's alpha sub y, where y is given by the derivative at 0. So it was part of the statement of that result. Classification of one-parameter subgroups.
And another question, with this, the commutability of this diagram, are we able to compute the tangent map of phi only using phi and the exponential?
We're not really able to compute it, but in all kinds of situations we are able to derive all kinds of interesting properties. For instance, one of the properties that we will derive, and this is the second half of what I wanted to do today, is that this will be equipped with a bilinear structure which turns this linear space into a Lie algebra. And in a similar way, this space is turned into a Lie algebra called the Lie algebra of H. And then this derivative will actually be bracket preserving. So it will be a Lie algebra homomorphism. Right? So that's clearly a very natural thing to hope for, and it's true. And we are going to... So this is the kind of properties that one can derive for the tangent map. Good. So I mentioned already that we are heading for the Lie algebra structure, and so let's start with this. Let's do this. And the idea is that the Lie algebra structure is a linearized version of conjugation. So what do I mean by this? Well, suppose that we have an element x in G. Then this produces a map, conjugation by x, which is a map from G to G. And it maps y to x, y, x inverse. Now G is a group, and so that means that the multiplication operation is associative, so I haven't put brackets here. But you could view this as either mu of xy, comma x inverse, or another expression. In any case, what you see is that this expression depends smoothly on both x and y. And what we are going to do now is we are going to take the derivatives both with respect to x and with respect to y. So we are going to linearize both in x and in y, and this will produce the Lie algebra structure on the tangent space and the identity element. Now, linearization means taking tangent maps. And we're going to do this in a particular order. The first variable that we are going to deal with is the variable y. Definition: we define add of x to be the tangent map at the identity of c of x. So basically what we're doing is we're taking the derivative at the identity element with respect to this variable. Right? What can we say about this? Well, first of all, this is a linear map. I mean, the conjugation is a smooth map from G to G. It maps the identity element to the identity element. And that means that the tangent map at the identity element is a linear map from the tangent space at the identity element to the tangent space at the identity element. Now, what more can we say? Well, so this is an observation, observe. If we take the conjugation by the identity elements, this is the identity map of the group G. So that means that its tangent map at the identity element is the identity map of the tangent space at the identity element. So that means that head of E is equal to the identity map of the tangent space. But there is more. Suppose that we take first conjugation by an element y and then conjugation by an element x, and suppose that we apply this to z. What do we get? We get x inverse, y, z, y inverse. And now because of associativity of the group, we can take the brackets wherever we like them. So we can first take these together. And then observe that this is the same as xy inverse. So in other words, this is the conjugation by xy applied to z. So the composition of two conjugations is a conjugation by the products. So the composition, this composition, is equal to the composition by the product. Now, so that means that we have a commutative diagram here. Commutative diagram goes like this. We have composition by y, conjugation by y, we have conjugation by x, and we have conjugation by xy. This diagram commutes. Also, if we look at what happens to the identity elements, then the identity element here is mapped to the identity element here. Identity element is obviously stable under conjugation, and this is mapped to the identity element here. Now, one interpretation of the chain rule is that taking derivatives at these points now produces a new commutative diagram of linear maps. Now, are you all familiar with that interpretation of the chain rule, or should I write it down? Okay. So, formulation of the chain rule. Suppose that we have the following situation. We have a manifold X. We have a map F. We have a smooth manifold Y. We have a map G to a smooth manifold Z. And we have a map H but from the smooth manifold X to the smooth manifold Z. And suppose that we have a point A which is mapped to a point B which is mapped to a point C. So really this is a map of pointed manifolds. This is a diagram of maps of pointed manifolds. And it's commutative. And now the chain rule tells us, so what we know is that H is G F composed with G. Right? And then we know, in such a situation, we know that the chain rule tells us that the tangent map of H at the initial point is really the tangent map of this composition. And the tangent map behaves very much like the total derivative, because in fact in local coordinates it may be identified with the total derivative, and then this is the tangent map at B of G composed with the tangent map of F at A. So this is really the derivative of G at the point F of A that I'm writing down here. And then this formula should be familiar to you. But what this says is precisely that we can apply the tangent map functor to this situation, and then we get tangent maps to the tangent map at C of Z. And then here we have the tangent map at A of H. And this diagram commutes. So if the chain rule may be formulated in the following way. If we have smooth maps of pointed manifolds, and we have such a commutative triangular diagram, then the associated diagram of tangent maps between tangent spaces is commutative as well. Right? This is a reformulation of the chain rule. And it basically says that taking a tangent map in the category of pointed manifolds is a functor. That's basically what this says. If you're familiar with the language of functors, then this is basically a reformulation, a kind of pedantic reformulation, if you like, of the chain rule. But it is a reformulation. But it's very useful to have this insight, because now we can immediately apply it to this situation, taking tangent maps at the identity map, and then we see that the corresponding map or diagram of adds is commutative. So this is add of x, and this is add of xy, and saying that this diagram is commutative may also be rephrased as add of xy is the composition of add x and add y. In other words, add satisfies the group homomorphism property, which is of course a very natural thing. Okay. So this is an important formula. And what I can do now is observe that this has the consequence. So, corollary is that add of x is an invertible linear map. Corollary, add of x as a map from TEG to TEG is invertible linear with inverse equal to add of the inverse. Right? I mean, this map exists because this inverse element in the group exists. And if we apply this formula from two sides, and we know that add of E is the identity map, we see that add of x is invertible with this as its inverse. So now, corollary, add as a map from G. So first of all, add maps G into the invertible linear maps of the tangent space at the identity element, and add as a map from G to this group is a smooth Lie group homomorphism. By the way, why smooth? Well, we have this conjugation structure dependent on two variables, smoothly on both variables, and what we are doing in order to get add is differentiating with respect to one of the variables, leaving the other variable free. So what remains is an object that smoothly depends on the remaining variable. This is all very natural. So it's really a smooth, a Lie group homomorphism is supposed to be smooth, but I want to emphasize this point. Now, a moment ago, we observed this very nice property of Lie group homomorphisms. It connects the exponential maps of both Lie groups. Let's see what happens here. So this is another corollary. Corollary. We have a commutative diagram because and the commutative diagram is this one. We have the exponential map of G going from the tangent space at the identity element. We have the derivative of this map. So now we are differentiating with respect to the second variable to the endomorphisms of this. This was the tangent space of that at the identity element, and now we should take the exponential map of this general linear group. So this is the generality. Okay? But we discussed an example. We discussed the example of the general linear group of a finite dimensional real vector space. And in that particular example, the exponential map corresponded with the classical exponential of a matrix. In other words, this exponential map is taking the exponential of a matrix. So let me write it down in this way. So if I apply this to a linear map here, then it means that I just take the classical exponential of that particular linear map. Now, obviously, this map is going to be of importance. Let's give it a name. Definition, we define little ad to be the tangent map at the identity of ad. And so now this is a linear map from this tangent space to the linear maps from the tangent space to itself. Of course, we want to know what this is in the example. Right? So now we are returning to the example again. Example that G is the general linear group of a finite dimensional real vector space. So suppose that X is an element of G, then conjugation by X is the mapping Y to this conjugate of Y. It maps the group to itself. It maps the invertible matrices to itself. But the conjugation can actually be carried out on the bigger space of all linear maps from V to V. So this conjugation, C of X, may be viewed as a conjugation defined on a bigger space and then restricted to G. So this conjugation on the bigger space is the map Y goes to X, Y, X inverse from the endomorphisms of V to itself. Now this map is linear in Y. This is linear. So what are we doing? We have a linear map. We restrict it to an open subset and we take the tangent map at the identity element. Now this is basically the total derivative of C of X at the identity element, which is the identity map of V. But C of X is the restriction of a linear map to this open subset, and the derivative of a linear map is the same linear map. So this is the same as C tilde of X. In other words, add of X is given by Y goes to X, Y, X inverse. And now we are in the situation. So this is as a linear map. Now we can differentiate with respect to X and the identity element. Let's do that. The derivative of add at the identity element, which is now apply this to an element X. So this is now add of X. What does add of X do? Well, we have to differentiate with respect to this element X at the identity element. Right? So by applying the Leibniz rule, which can be done in this situation because we have this multiplicative structure here, or you could also say by applying the chain rule and partial differentiations, this derivative can now be calculated. It's really Y maps to xy coming from differentiation with respect to this variable, and then minus yx coming from differentiation with respect to that variable. In other words, this is just the commutator brackets of x and y. So in this classical example, we produce here the commutator brackets as a kind of second order derivative, mixed partial derivative of the conjugation structure. And now the idea is, of course, define the Lie algebra structure in general by using the derivative of this at, by using this little at. So this is the final definition for today, and then next week I'll continue the further build-up of the theory. So define the bracket structure from here. The bracket structure on the tangent space by x comma y, brackets of x comma y is add x, defined in general in this fashion, and then applied to y. And then next time I will show that this defines a Lie algebra structure on the tangent space, and this is called the Lie algebra of the Lie group. And then we will develop some further properties. So this finishes the lecture for today.